we're given a polynomial. This notation means this polynomial has integer coefficients. And so if we have a prime p, if this prime divides a0, also divides a1, all the way up to ak minus 1. And obviously k is less than or equal to n. And except p doesn't divide an, and p squared doesn't divide a0. Then we want to show that there exists a polynomial with integer coefficients, so that and the degree of the polynomial is not only greater than or equal to k, right, the same k here, but also the polynomial is irreducible over integer. So what do I mean by that? So reducibility, for example, a polynomial x squared, for example, plus 1, right? It is irreducible over real numbers, right? Obviously irreducible, but it is reducible over complex numbers. Right? The reason is because that is equal to x minus I times x plus I, right? Obviously. So we have, first, this polynomial has real number coefficients, but somehow here I have complex number coefficients. So that's why I must specify which number system we're talking about, right? So, of course, x squared minus 2, right? It is a polynomial with integer coefficients, right? So it is not reducible over integers, but it is reducible over real numbers, because that is equal to x minus square root of 2 times x plus square root of 2. Now we have coefficients of real numbers. Right? So that's why we have to specify. And so by reducibility, I mean we have to write it as a product of several polynomials, right? Where each polynomial has the degree of at least 1, right? So this doesn't count. So, for example, it can be written as 2 times half of x squared minus 1, right? So since 2 is a polynomial of degree of 0, so that doesn't count, right? So this is not reducible. Right? I don't consider this reducible, for example, over the whatever. So we must require. So in that case, so here h can be degree of 0. That is fine, right? So the background of this problem is that it is a generalized version of Eisenstein test. So I will in the future I will prove the Eisenstein test. But first, let's prove this test. Right. So if the polynomial is already irreducible over integers, then we're done. Because the degree is n is bigger than or equal to k, right? Degree is bigger than or equal to, then we're done, right? Right, so if f is already irreducible over integers, then we're done. Now if f is reducible, right, over integers, in other words, it can be written as a product of several polynomials where each polynomial has the degree of at least 1, right? Let's call that g of x times f1 of x times f2 of x, all the way up to fm of x. All right, so none of the polynomial is constant polynomial, right? At least degree of 1. So in that case, let me just write down a0. I want to represent a0, right? So a0 must be the product of the constant term of each of the polynomials, right? Let's look at constant terms. Now the constant for polynomial g, right? What's its constant? Let me just denote it as b0. Right? constant for f of 1, denoted as d1, right? F of 2, constant term is d2, all the way up to f mx dm. Right? So therefore, the constant a naught, right? Constant of this polynomial, right, must be the product of these ones, right? B naught, D1, D2, all the way up to Dn. Now, given that P divide A naught, right, meaning P divide this product, right? So meaning P has to divide at least one of these integers. At least one. Could be 2, could be 3. Right? Could be all of them altogether. But also because P squared doesn't divide A naught. Yeah. Then we can claim that P divides exactly one of them. Exactly one of them, right? Cannot divide 2 or 3 or more. If P can divide 2 or 3 or more of them, that means P squared has to divide A naught, right? So without loss of generality, let me just say P only divides B naught, but at the same time does not divide D1 times D2 all the way Dn, right? Without loss of generality. Right. Now I can let f1 x, f2x all the way times fmx. I can let this equal to, let's just denote it as h of x, right? So that g of x, right, can be written as let me just use br xr in descending order, right? The power keeps descending, plus all the way down to b naught, constant term, right? Constant term gx. And let me just write h of x, or h of x, as cs, right? Cs, x to the s, descending order, all the way down to c naught, right? So therefore, like I said, h is the product of these ones, right? And the product of the constant terms of these ones is just d1, d2 all the way up to dm, right? In other words, constant c naught is in fact d1, d2 all the way dm, right? So in other words, P does not divide C naught. Right, let me just, I'll be using this fact, right? This is a key fact. And so far I've established f of x. If I forgot to mention that the existence of such product of series of polynomials. So we can always break this polynomial down into a product of several irreducible polynomials. Every one of them is irreducible over z. This is pretty much like the fundamental principle, arithmetics, when you rewrite an integer into a product of several primes, unique way. This is very similar. The existence, no problem, right? So every one of them is irreducible. The only job now is to prove that G is degree is greater than or equal to K, right? In other words, to to prove R is, so claim R is bigger than or equal to K. Right? So far we've established that P cannot divide C naught, but P can divide B naught. Because like I said, once we rewrite f of x into g times h, right, we can say that the constant term, a naught, must be written as b naught times c naught. Since P divides a naught, therefore P either divides b naught or c naught, right, or both, but cannot happen. Only divide b without loss of generality, because P squared doesn't divide a naught, right? Therefore, only divides one of them. Without loss of generality, we say divides b naught, but doesn't divide c naught, right? That's why. So here's our claim, right? So if otherwise, prove by contradiction. If R is less than K, what's going to happen, right? Is there a contradiction? So right now we have, since P doesn't divide a naught, so P doesn't divide an, right? P doesn't divide an. And also an can be written as BR times CS, right? That's the first term, right? BR times CS. So therefore, P does not divide BR. Right? This is obvious, right? Does not divide BR. And how can I, so that means even if P divides, even though P divides B naught, perhaps also divides B1, right? Perhaps also divides B2, right? Perhaps also divides BU minus 1, right? But P does not divide BU, where U is greater than or equal to 1 and less than or equal to R. So what I'm trying to say is that one thing we're sure is that out of all the B naught, B1, B2, all the way up to BR, right, we already know that BR is not divisible by P, right? There could be more member that cannot be divided by P, right? So so what I'm trying to say is that out of these many numbers, there must be the first guy that cannot be divided by P. Let's call that first guy BU, right? Before BU, everybody can divide it by P, right? BU is the first guy, cannot be divided by P. Let's call it BU. Of course, U could be equal to R exactly, or could be less than R, right? Possible. Now, so generally speaking, how can I of course, R is less than K, right? This time I want to look at AU. Right? I want to look at AU. So AU can be written as B naught times CU plus B1 times CU minus 1, all the way up to BU minus 1 times C1 plus BU times C naught. Right? The reason is because somewhere in here we have we have AU times x to the power of u, right? So where does that come from? That comes from all the possible combinations out of those two polynomials, right? Perhaps it's somewhere this constant times the other constant. So as long as the subscripts of the constant add up to u, right? That's a possible combination, right? So this times that, that times this, or every, so every possible combination, we just add them together, gives us the constant AU. Right? So because can P divide AU? Can P divide AU? P can divide A naught, can divide A1 all the way, can divide AK minus 1, but cannot divide AN. Right? So U is less than R, strictly less than K, right? So U is strictly less than K. U could be K minus 1, could be, so yes. Yes. P can divide AU. Right? Also, P can divide B naught, P can divide B1, P can all the way, P can divide BU minus 1, right? So P can divide this term, P can divide this term, P can divide this term, right? P can also divide this term, right? So how about this term? Yes. So therefore, P can divide it, because this is a linear combination of this, can divide BU times C naught, obviously. So P can either divide BU or can divide C naught, or both. Can it be both? No. Right? So because since P doesn't divide BU, right? Like I said, BU is the first guy that cannot be divided by P out of those guys, right? So P can only divide C naught. Contradiction. All right, like I said earlier, I said I'm going to use P doesn't C naught. P doesn't divide C naught, the fact, right? Now P can divide C naught. Contradiction, right? So here's the key step, right? So recall, how did I get this one, right? How did I get this result, right? Why does P divide B naught? Right, it's because let's recall, because A naught can be written as, right? It's all because A naught can be written as B naught times C naught, right? That's where the constant term comes from, right? It's a product. F is a product of these two polynomials, right? Constant term, right? That's constant term. Well, product gives me this constant term, right? Because remember, recall, P divides A naught, right? Divides A naught, right? That's therefore P divides B naught or C naught or both. Cannot be both. Because it says P squared cannot divide A naught. Cannot be both. Therefore, I say without loss of generality, P divides B naught but not C naught. Right? That's the key step. Then I somehow reached this conclusion. P divides C naught. Contradiction. That's why. And so where does the contradiction come from? Well, it's all because I made the false assumption. Proved by contradiction, I assumed that R is strictly less than K, which reached this contradiction, right? So that means my assumption is false, right? R cannot be less than K, therefore my claim is correct. Right? R is greater than or equal to K. Right? So my job is done. So the degree of this G is really at least K. Right? Also, G is irreducible over integers. right? Because like I said, right, every polynomial can be written as a product of several polynomials where each polynomial is irreducible over the given number system, field, ring, or whatever. Right? The existence is guaranteed. Right? The job is done.